This is slide number 39 and I am your presenter Asloob Mudassar. More about Kirchhoff boundary conditions. It is a well established fact that if the solution of a three-dimensional wave equation vanishes on any finite surface element, it must vanish in all the space around that element. So u and its partial derivative must vanish in opaque region according to Kirchhoff boundary conditions. Then according to these must also vanish in the region of the clear aperture, which contradicts the known physical conditions. So according to the Kirchhoff, as u and its partial derivatives should vanish in the opaque region, so according to the above statements, then it should also vanish in the clear aperture, which contradicts the known physical conditions. The second is that u and its partial derivative must vanish in the open or the clear region as the observation point P naught reaches it, which contradicts the second Kirchhoff boundary conditions, according to which the field before and after the clear aperture should be the same. So you see that the second boundary condition of the Kirchhoff was that the field before the clear aperture and after the clear aperture should be the same as if the aperture is not present, and you know that if we bring the point P naught closer to the aperture, then the field becomes equal to 0, which contradicts the known physical conditions. So Sommerfeld correction are here. According to the Kirchhoff scalar diffraction theory formula, equation 32 is correct. The derivation of equation 32 was based on the following assumptions. The scalar diffraction theory is valid. Both u and capital G satisfy the homogeneous scalar wave equation. Number 3, the Sommerfeld radiation condition is satisfied. The formula, the scalar diffraction formula in equation 31 that we have derived based on Kirchhoff's conditions, were based on these three assumptions. That is, the scalar wave theory is valid, both u and g satisfy the homogeneous scalar wave equation, Sommerfeld radiation condition is satisfied. Rayleigh and Sommerfeld suggested two sets of Green's functions to correct the scalar diffraction theory of Kirchhoff. You know that in the Kirchhoff theory the two assumptions were made and both assumptions were incorrect. Now you see that in order to correct them, Rayleigh and Sommerfeld suggested two Green's function to correct the scalar wave theory, scalar diffraction theory. So you see that, let me first of all explain this figure. In the figure you can see that there is a point source P naught, P2, there is a point source P2 which is generating spherical wave all around, and part of that spherical wave is also falling on the clear aperture S1. So you see that P naught is the point of observation, and on the another side we have a P naught prime, which is the mirror image of a point P naught. The P naught is located with respect to P1 at a distance R01, and similarly P naught prime is located at a distance R01 prime with respect to P1. So R21 is actually the distance between P2 and P1. So P1 is located in the clear aperture. So having this geometry in mind, you see that in the Kirchhoff model we have assumed that a point source, that is the Green's function, exists at point P naught. Here we are assuming two Green's functions. One is sitting at point P naught, the other is sitting at P naught prime, which is the mirror image of a P naught. So we shall have two Green's functions now in this problem suggested by Rayleigh and Sommerfeld. These Green's functions are given in equation 44 and 45. In 44, the point P naught prime is actually out of phase with respect to P naught. Both are generating spherical waves, but P naught prime is being a mirror image of a P naught. But you know that in this case we are assuming that P naught is generating waves out of phase with respect to P naught. So we have a negative sign over here. So we have also denoted that Green's function as G minus of P1 at the position P1. We have written down the value of the Green's functions at point P1. One Green's function is at P naught, the other Green's function at P naught prime. So due to these two Green's functions, we have written their contributions at P naught, that is e to the power iota k r01 over r01 minus e to the power iota k r01 prime over r0 prime. This negative sign means that the source at point P naught prime is out of phase with respect to the source at point P naught. Now we have G plus at the contribution of the Green's function, the two Green's functions at the point P1. We have denoted it plus sign because we are assuming that both the contributions from both Green's functions, one at p naught, the other at p naught prime, are reaching the point p1 in phase. So we have a plus sign over there in equation number 45. So e to the power iota k r01 over r01 plus e to the power iota k r01 prime over r01 prime. So one Green function with negative sign means that one of the source at p naught prime is out of phase with respect to p1 with respect to the source at p naught, and g plus means that both sources, both Green's functions are operating in phase. So in addition to the point sources p naught being existed and the point source p naught prime, which was mirror image to the point source at p naught, for the Green's functions g minus, the point source p naught prime was 180 degree out of phase with respect to the phase of the point source at p naught, and for g plus both sources were in phase. So equation 44 and 45 are the values of the Green's functions g minus and g plus at the arbitrary point p1 located in the open aperture S1. Now we have to calculate the directional derivatives of g minus and g plus 1. We have already calculated these directional derivatives in one of the slides. Here we are giving the partial derivative of g minus with respect to n without explaining them. In equation 46, and so in equation number 47 we have the partial derivative of g plus with respect to n, and without explaining them we have written down because we have already explained them many times. Using the fact that r01, that is the absolute value of r01 is equal to the r01 prime, because both are mirrored images, that is p naught and p naught prime are mirrored images with respect to the clear aperture. That's why we have written. And also cos of the angle between the n, the unit vector n and r01 will be equal to the 180 degree times the unit vector between the angle between n and r01 prime. So the angle between n and r01 and the n and r01 prime both are 180 degree out of the phase. We have a negative sign between them. So cos of n hat comma r01 is equal to minus times the cos of n hat comma r01 prime in equation 48. Now assuming that the point of observation and the point source are many optical wavelengths away from the diffracting aperture, because you know that this is the condition that we have to assume in order to write down useful information. So here we have reciprocal of r01 is less than k, and 1 over reciprocal of r01 prime is less than k. These two conditions have also been explained in one of the previous slides, and this is equation number 49. So using the relations given in equation 48 and 49, and we can write equations 44 to equations 47 in the following form. So you see that g minus, that is the Green's functions minus Green's function at point p1 becomes equal to 0 when we consider the above conditions, and g plus becomes equal to 2 times of e to the power iota k r01 over r01. So you see that this becomes equal to 2 times the Kirchhoff Green's function. So this simple g which we have written is actually the Kirchhoff Green's functions in equation number 51. So g plus at p1 under the above conditions will becomes equal to 2 times the Kirchhoff Green's function at p1. Okay, now the partial derivatives. We are also using the above conditions on these partial derivative. So the partial derivative of g minus with respect to n will be equal to 2 times the partial derivative of the Kirchhoff Green's functions with respect to n. This is stated in equation 52. And in equation 53 we have that the partial derivative of Green's function g plus with respect to n will be equal to 0. So you see that we have evaluated Green's functions g minus, then g plus in terms of the Kirchhoff Green's functions, and then we have evaluated the derivative, their respective derivatives, that is the derivative of g minus with respect to n in terms of the Green's function, which is equal to 2 times the derivative of the Kirchhoff's Green's function, and then we have also evaluated the derivative of the partial derivative of g plus with respect to n at point p1, that is equal to 0. Now Rayleigh and Sommerfeld used g minus and its partial derivatives in the scalar diffraction formula of equation 32 and obtained the results. So you see that we have written equation 32 with the Green's functions over here. You can see that we have double integral over s1 plus s2, and we have g minus with the partial derivative of u with respect to n minus u into partial derivative of g minus with respect to n, and with multiplied with the surface element ds. Now you know that substituting the values we have calculated above, g minus is equal to 0, so we are left with only this quantity, and of course the partial derivative of g minus with respect to n is equal to 2 times the partial derivative of the Kirchhoff g with respect to n. So 2 will cancel out the 1 over 4 outside the integral, and we have a minus 1 by 2 into the double surface integral over s1 and s2, and the integrand is now u, and the partial derivative of g with respect to n and the surface element ds. This integral is now we are referring to as u1 of p naught, that is the contribution at point p1 due to at on the surface s1 only. You see that we have indicated only the surface s1, so this is for the surface and on the clear aperture. So the clear aperture is contributing at the point p naught. So this is given in equation 4. Now where is s2? Where is the contribution of s2? This is explained below. For the first Rayleigh Sommerfeld solution that we have written in equation number 54, we assume that u is equal to 0, but its partial derivative is not equal to 0. You know that Kirchhoff assumed that u and its partial derivative both are 0 behind the opaque aperture. But you know that here we are not using these two conditions, we are using only one of the conditions, and the condition is that here we are assuming for the Sommerfeld solution 1 that u is equal to 0, but its partial derivative is not equal to 0, and you know that according to that one the surface integral over the s2 will become equal to 0, because here u is equal to 0. And you know that we have only satisfied one condition of the Kirchhoff. Both cannot be 0 because we have chosen two Green's functions, and they have provided us the opportunity that we can recall that only one of them, that is either u is equal to 0 or partial derivative of u is equal to 0. But you know that here we have assumed that u is equal to 0. That's why we have set the double integral over the opaque region equal to 0. Now we are using g plus and its partial derivatives. The following diffraction formula was obtained. So you know that this is the same formula as previously written, but now it is written for g plus Green's function. You can see that we have the double integral over the two surfaces s1 and s2. And here if you substitute the value of these Green's functions, what you get is that capital partial derivative of g plus with respect to n is equal to 0. So setting the partial derivative of g plus equal to 0, we are left only with the g plus and partial derivative of u with respect to n. But g plus here is equal to the Kirchhoff g, you know. So we have 2 times of the Kirchhoff g. So 2 will be cancelled out, the 1 over 4 over there, and we have 1 over 2 by the double surface integral over both the surfaces s1 and s2, and in the integrand is g and the partial derivative of u with respect to n multiplied by the surface element ds. So you know that this right hand side will be regarded as the u2 of p naught. That is the second solution of the Sommerfeld. That is the second Sommerfeld solution we have regarded it as. So and we have written, you know, that only the surface integral over the surface s1 only. We shall explain why the surface integral s2, where is the contribution from the surface integral s2. But here you know that in equation number 5 we have the second Sommerfeld solution. For the second Rayleigh Sommerfeld solution, that is u2 of p naught, we assume that u is equal to 0, u is not equal to 0, but its partial derivative is equal to 0. So you know that if you put partial derivative of u is equal to 0 in equation number 55, you will see that this integral becomes equal to 0. So that's why the integral over s2 becomes equal to 0, because here the partial derivative of u with respect to n is equal to 0, but u is not equal to 0. U was equal to 0 when we were writing the first solution of the Sommerfeld solution. And in that case the double integral over s2 was 0, but here the double integral in case of using the Green's function 2 or the Sommerfeld solution 2 is 0 over the surface s2, because we are assuming that u is not equal to 0, but its derivative is equal to 0. So you see that we are not setting on while writing the Sommerfeld solution 1 and the Sommerfeld solution 2, we are not assuming both u and its partial derivative equal to 0. We are assuming that one of them is equal to 0 at a time, the other is not 0. So that's why we have set the contribution after the opaque region equal to 0 in using both the Sommerfeld solution 1 and 2. And we have written only the contribution of the surface is S1 as S1 on the point P on the point of observation P naught. Now let's summarize the above statements. Use of Rayleigh-Sommerfeld Green's function G minus is equivalent to establish that u is not equal to 0 but its partial derivative is equal to 0. These two hold behind the opaque aperture surface S2. That's why the contribution from the surface S2 is equal to 0. Now use of Rayleigh-Sommerfeld Green's function G plus is equivalent to establish that u is equal to 0 and its partial derivative is not equal to 0. These two conditions hold behind the opaque aperture surface S2. That's why the contribution after the S2 will be equal to 0 because one of them is equal to 0. The Kirchhoff diffraction formula equation 33 can be obtained by taking the arithmetic mean of two scalar diffraction formulas u1 of P naught and u2 of P naught obtained by Rayleigh and Sommerfeld. So you see that the Kirchhoff diffraction formula, which was written using wrong assumptions, now we see that the Kirchhoff formula can still be written if we do the arithmetic mean of the form of the two Sommerfeld solutions u1 of P naught and u2 of P naught. Using modified Green's functions, Rayleigh and Sommerfeld were able to remove the inconsistencies in the assumptions made by Kirchhoff by establishing that either u is equal to 0 or its partial derivative is equal to 0 behind the opaque region of the aperture, and that both cannot be 0 simultaneously. It is therefore not very surprising to find that even in the presence of inconsistencies, the Kirchhoff diffraction formula yields fairly accurate results matching with the experimental results, especially when the size of the diffracting aperture is much greater than the wavelength of light. The Rayleigh-Sommerfeld diffraction formula, equation 54 and equation 55, can be written in explicit form by substituting functional values of u, capital G, partial derivative of u, and the partial derivative of g. So let's use their functional values in the formulas that we have derived earlier in equation number 54. So substituting these values simply, we have come up at equation number 56. The last expression you can notice that we have u1 of P naught is equal to a over iota lambda, the double surface integral over the surface S1, and within the integrand we have e to the power iota k. Within the parenthesis we have r01 plus r02 and divided by r01 into r21 and multiplied with the cos of n r01 and the surface element ds. So you see that we have written the solution which we have derived in number 4 in the form of now in the form 56 in the explicit form, representing the actual values, giving the actual values of u, g, and its the partial derivative of u and the partial derivative of g. Similarly, we can write for the second solution. The explicit form for the second solution is now given in equation number 57. So here you see that we have a negative sign and a over iota lambda and the surface integral very much the same, but you see that here we have a cos of n hat and r21, not r01. The Fresnel Kirchhoff diffraction formula of equation 41 and the Rayleigh-Sommerfeld diffraction formulas derived in equation 56 and 57 can be combined into single formula for quick comparison as given below. So now we are combining the three formulas, the Fresnel Kirchhoff and the two solutions of the Sommerfeld solutions, Rayleigh-Sommerfeld, combined in equation number 58 by using chi over there. So you see that in the argument we have chi and the rest of the quantities are the same in all the three formulas. So what is chi? Chi is equal to cos of n r01 minus cos of n hat r21 divided by 2. This is actually the Fresnel Kirchhoff solution. in the Fresnel Kirchhoff solution, if you assume this value of chi, then the solution, if you use this value of chi in equation number 52, then you come up with the solution of a Fresnel Kirchhoff solution. Now the Rayleigh-Sommerfeld solution 1, you have to use chi is equal to cos of n hat comma r01. And for the Rayleigh-Sommerfeld solution 2, you have to use the value of chi is equal to minus cos of n hat comma r21. So you see that the equation number 52 is a brief version of the three solutions if you remember the corresponding values of chi. If the point source P naught illuminating the diffracting aperture is located at a very large distance such that the wavelengths reaching the apertures are plane waves, then you know that cos of n comma r21 is equal to minus 1 and chi would then take the following form. So here we assuming that over source, point source P naught is at a very large distance so that the spherically diverging wavefront reaching the clear aperture are no more spherical but plane wave can be assumed for them, and for that case we have cos of n vector comma r21 will be equal to minus 1, and in that case the chi will take the following form. So you can see that this is the special case when the source is point source P naught is at a very large distance and the wavefronts hitting the clear aperture are the plane waves. In addition, now we are assuming further that in addition to the diffracting aperture being illuminated by plane wavefronts, if the point of observation is also located at an infinite distance or in the far field from the diffracting aperture, then cos of n hat comma r01 will be equal to 1 and the chi becomes equal to 1 and the three solutions will be identical. So you see that the three solutions will be identical to each other if in addition to the condition that the point source P2 is at infinite distance, and we have written this chi as given in equation number 60. If we further assume that our point of observation is also at a very large distance or in the far field, then the cos of n comma r01 is also equal to 1, and you know that all the chi in all the three cases will be identical. If the point of observation approaches the refracting aperture, the two theories yield different results. Rayleigh-Sommerfeld theory. Two Green's functions in the form of 2 point sources we have used. The refracting aperture is treated as a planar surface. So in the speciality of using the Rayleigh-Sommerfeld 2 Green's function is that in the clear aperture, since we have two Green's function as point sources sitting on the one is sitting on the point of observation P naught and the other is sitting on the mirror image of the point of observation P naught, due to these two Green's functions contributing at the clear aperture in such a way that the aperture appears as planar to these two Green's functions. So in the Rayleigh-Sommerfeld solution, the diffracting aperture is treated as a planar surface, whereas in Fresnel Kirchhoff theory, since we are using only one Green's function, so according to that Green's function, the wave contributions due to that Green's function reaching at the clear aperture will not be plane but will be curved. So single Green's function as the point source located at the observation point, and due to that one the diffracting aperture takes the shape of the curved aperture. In practice, planar diffracting apertures are more common in optics, and thus the use of the Rayleigh-Sommerfeld diffraction formula is preferable. Let's write the diffraction formula in equation 52 in another form to review some more additional physical features. So we have written the formula in 58 in another form. So look at this form. So we have, you know that we have A over, in the second step we have the surface integral over S1, A over lambda, and then e to the power iota k. Within the parenthesis we have R21 minus pi over lambda, because iota has been written as minus pi over lambda in the exponent, and we have divided by R21, and we have also separated the contribution of the point source due to the Green's function sitting on the point P naught is equal to e to the power iota k R01 over R01, and the chi is there, you know. So we have written this solution now as in this form: u of P1 into e to the power iota k R01 over R01. where u of p1 represents the complex amplitude of the secondary source located at p1. So you know that this u of a p1, which is contained in the integrand in the integral of equation number 61, we say about this one that this is the complex amplitude of the secondary source located at P1 within the clear aperture. The integral over the clear aperture S1 sums up the contribution of these secondary sources u of P1 into e to the power iota k r01 over r01 at the point of observation P0. The expression for the amplitudes of the secondary sources is given by. So this is the amplitude of the secondary sources. Amplitude of the secondary sources is complex. Now we are saying something about this equation number 62, that the amplitude of the secondary sources is complex. You can see that on the right hand side we have complex quantity directly proportional to amplitude A, inversely proportional to the wavelength of the physical source, and due to minus pi by 2 present in the exponent, we have this leads to the phase of the incident wave by 90 degree. So now we are writing equation 61, that is this one in another form. Let's see how we represent 61 in another form. The diffraction formula equation 61 can be written as u of p naught is equal to double integral over the surface S1. So we have written two quantities kappa as a function of p naught comma p and u prime of p1. So where kappa of p naught comma p1 is equal to 1 over iota lambda e to the power iota k r01 over r01 multiplied by chi. And chi, we are substituting the value of chi from the first solution of the Rayleigh-Sommerfeld solution. So we have on the right hand side in equation number 64 cos replacing chi. So this is for the first Rayleigh-Sommerfeld solution. So we have written in 60 number 5 the amplitude which we have represented in equation number 63 as u prime of p1. So in equation 65 we have u prime of p1 is equal to a e to the power iota k r21 over r21. So kappa that we have written as a function of p naught p1 may be regarded as the impulse response of the system. That is, if u prime of p1 is chosen to be a delta function, that is a point source, then u of p0 will be equal to kappa. So you see that in this equation, in equation 16 number 3, if you choose u1 of p1 as a delta function, that is a point source located at p1, then you know that u of p0 will be equal to kappa. So the contribution the field at the point p0 will be equal to kappa. And kappa, you know that if you will be regarded as the impulse response of the system. So if you have a point source at the clear aperture, then you have a contribution at the observation point equal to kappa. So such a condition in which you have u of p0, that is the contribution at the point p0 is equal to kappa, is due to the fact that we have used p1, that is the point on the clear aperture, as the point source represented by delta. The diffraction formula of equation 60 number 3 can be written in the form of convolution integral only for space invariant system. So you see that in the next, in the coming slides, we shall be writing this equation, that is 63 equation, in terms of the convolution integral. Here this cannot be written in the convolution integral, but there we shall write them and we shall explain the conditions also. So the diffraction formula equation number 3 can be written in the form of convolution integral only for a space invariant system. This will be explained in future. Whenever needed, we shall keep on using Rayleigh-Sommerfeld solution 1 as the diffraction formula. So this is the end of slide number 39.